Hello, everyone, and welcome to Chapter 2, Part 1. In this chapter, we are going to discuss chemistry, as this chapter is called The Chemical Context of Life. The first half of it will focus mostly on atomic structure, electrons, that kind of stuff, subatomic particles. The second half, we will focus on the bonding, chemical bonding. Now, as we started, just as a reminder, nothing worth having comes easy. Now, as you study, make sure you use these objectives in a meaningful way. One of the things, can you actually distinguish particular aspects of those? Can you do that verbally? Can you actually verbalize that? That is a great way of knowing that you know it. There is one thing is to think you know it. There's another thing to know you know it. And that is part of the problem that students have. So I want to help you guys do that. Now, as we begin, let's just talk about matter. Matter is really anything that has mass takes up space. If you have mass, you take up space, you matter. Matter comes in three major states. We know there are others. Solid, liquid, and gas, and they are based, we can describe them about how tightly packed their particles are. And so if they are tightly packed, for example, we might see that constant shape and volume that we would find as solid is there because of the tightly packed particles. Liquids are a little bit more loosely packed, so they do take on the shape of the container they're in, but though they move, they are packed enough to maintain a volume. Now, gases are so loosely packed, they're just loosely associated. They have no defined shape or volume, but you can go out there and compress it. Now, what we want to talk about is the difference between elements, molecules, and compounds. Now, kind of think about the element, the molecules, and compounds. I've got a way I always like to describe this. Let's imagine we're going to our favorite ice cream shop. Each flavor of ice cream can be thought of as the element. And a molecule would be if I went and ordered 2 or more scoops of ice cream on my ice cream cone. Now, I can order 2 more scoops of the same flavor or 2 more scoops of different flavors. Now, the elements are the thing. You can't break it down anymore. What you'll see is I got only atoms of that element. It's purely carbon atoms. If it's elemental carbon, it's purely sodium atoms. If it's elemental sodium, it's purely chlorine atoms. If it's elemental chlorine. And I can combine these together to make molecules, 2 or more atoms bonded together. And I should say 2 or more atoms because at least 2, if not more. And a compound is a molecule made up of different atoms of different elements. Now, what I like to do, guys, is kind of discuss it like this. Let's say that I have H2, I have O2, I have H2O, and I have CO2. So there are 4 molecules. Now, these are all molecules because we have 2 or more atoms bonded together. 1, 2, okay, 1, 2, 3, 1, 2, 3, 1, 2, 1, 2, okay? 2 or more atoms bond together. These are all molecules. Now, that in itself qualifies every last one of these to be in the molecule club, okay? These would all be molecules. Now, remember my analogy discussing the ice cream, that I could go get 2 or more scoops at the ice cream shop, ice cream parlor. Now, I could get of the same flavor or mix and match flavors. Now, we're still getting an ice cream. We're still getting 2 or more scoops. So what I like to do is mention that compounds, okay, compounds, these are 2 or more atoms of different elements. So it is like we are getting different. It's like this time it said we had like 2 scoops of vanilla, 2 scoops of chocolate. Now I got vanilla and chocolate. Here it's like I've got strawberry and 2 chocolates. Okay. And so we're compounding them together in a fixed ratio. Makes a compound. Okay. Now, Be able to recognize based on a chemical formula, for example, H2SO4 would be a compound. NH4 would be a compound. NaCl would be a compound. Okay, but N2 that would not be a compound. That would be just a molecule. Okay. And that's kind of things I like to look at here to help you guys understand. Now, what I want to do is make sure we understand that it is the molecules and compounds have different properties than what makes them up. That was an example of emergent properties we saw in chapter 1. All right. Now, what I want to help you guys understand too is that 4 elements in order of, we might say, OCHN, oxygen, carbon, hydrogen, and nitrogen make up by far most of a living human being. Okay, most of your body is made up of 4 elements. 96.3% of your body, which includes the water right now in your body. The rough percentage of this would be about 96.3%, including water, are these 4 atoms. Now, we are 2/3 water roughly, so that gives us an idea of what's going on here. Now, some of these are needed in less things like calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. Even less are needed as a trace element. Combined, all the trace elements are about 0.01% of the entire mass of a body. Now, you think iron is amongst these added together. And iron, for example, is used to make your hemoglobin. It's also used to make your myoglobin. And all the muscles, all the red blood cells, about 25 trillion red blood cells you had, each with 250 million hemoglobin molecules in it. Each hemoglobin has 4 irons, all the myoglobin. All of that iron, and still added together, it is only a trace compared to everything else. Now, that's a lot of hemoglobin when you really think about it. So, but those are now trace elements can have a very big impact. Like iodine, if you don't have it, you get goiters. You may have heard of selenium poisoning, things like that. These things only need to be in a very small amount. Now, what I want to talk about now are the subatomic particles. Now, let's imagine my subatomic particle petting zoo for a minute. I've got a subatomic particle petting zoo, and in my petting zoo that we have, I've got the center of attention here, my nucleus of my subatomic particle petting zoo, where I have protons. And protons being in the nucleus, we're going to call them P plus because they have a positive charge. They weigh 1 AMU. And then as well, I have neutrons, in which we're going to call NO because they have no charge. They have a neutral charge. And they are in the nucleus. They also weigh 1 AMU. Now, out here around it, I've got my other animals, okay, in my petting zoo. And I've got my electrons. Now, let's think of protons. This would be like my proton elephant and then my neutron hippo. They both weigh quite a lot. My protons weigh 1 AMU, 1 atomic mass unit, and my neutrons weigh 1 AMU or 1 atomic mass unit. But my electrons are going to be like a flea. They don't weigh much at all. They weigh something around a minor fraction. There's the value is not one I ever bothered to memorize. The mass of electrons in kilograms is 9.109 to 10 to the negative 31 power. It weighs about 0.000548 atomic mass units. It weighs barely a fraction of what any of these things weigh. So little. Now, it's out here in what is called an electron cloud in the orbits that exist in the cloud. Now, because there could be some other electrons whiz banging around, okay, this electron cloud, we could say the electron cloud surrounds some other electrons and the nucleus, so we could say that it contains everything, okay? Now, what I want to help us understand is the differences in protons and neutrons are in their charge, not their mass. Now, and they're both located in the nucleus, protons and neutrons. They both weigh 1 AMU, and they both have different charges, though. Protons actually have a charge that's positive, a +1 charge, whereas neutrons have no charge, they're neutral. So a neutron walks into a bar and the bartender says, "What can I get you?" The neutron says, "I'll have a beer." And the bartender says, "Sure thing, but for you, no charge." The electrons are negative. Now, what I want to help us understand is this can impact a lot on the atom. We'll talk about that. Now, here's some models to help us kind of understand what's going on. Electrons sitting in a shell. And then here we got them. They're just out here. And it's a cloud of negative charges. They're whiz-banging around the nucleus. Okay? Now, electrons, protons, and neutrons. Electrons are in the electron cloud. Each one, they're set up in their orbits. They have roughly no mass, and they have a -1 charge. And I know I could have easily one of these days. There we go. I'm just going to hit the save button on that. I thought I hit the save button on that. There we go. I'm going to hit that save button on that. Now, what I want to talk about is, guys, your protons and your neutrons are both in the nucleus. They both weigh 1 AMU, but we're going to see protons have a charge of +1, where neutrons have no charge, okay? Now, let's talk about your periodic table and what's going on it. Now, the tiles of the periodic table, each individual thing on it. There is information to glean. And the information that we want to glean on that, let's just pick a friend of ours here. Let's pick nitrogen. And let's just say we got about that. Let me just double check. It's pretty close. I never like to write anything completely. Oh, look at that. Its nitrogen is 14.007. I always think about 007 liking his gin, but he liked vodka martinis, shaken not stirred. Okay. Now, what we're gonna see is this tells us some information. There's a number here. This number is always the lowest number. It is called the atomic number. It is by that number here that we define the element by. That element has a number that defines it. All atoms of nitrogen have an atomic number of 7. Now, this tells us the number of protons that this atom has. Now, it also, by the way, will tell us the number of electrons. Now, real quick on a side here. Let's say I had -1 and I had +1. And I were to add them together, we would see that would equal 0. Anytime positives equal negatives, we would have a charge of 0. We would have 0 would be our answer. Because protons and electrons always equal, the number of protons must always equal the number of electrons, always, always, always on the periodic table. Now, it will be that ions will break the rule, but on the periodic table of elements, it is going to be this rule. Now, what I want to help you guys understand here, okay, is that with these two guys interacting with each other, what I want to help us understand is all atoms on the periodic table have a charge of 0. Now, of course, we also have this thing here. That's our atomic symbol. Atomic symbols, the first letter is always capital. So if you ever happen to have something like helium or neon where you have two, always first is capitalized, second is lowercase. The atomic symbol in this case is for nitrogen. And then here we have a very important number, which is also added here, is called the atomic weight. Some will also call this a mass number. I like to call it the atomic weight. That is what most the periodic table I use will call atomic weight. Some people call it call it a mass number. And what this is the average number, the average mass, okay, of all atoms and their isotopes, and we'll talk about that. Now, we can glean a lot of information from this, okay? And we're going to talk about that in just a minute. Things we can glean from that. We're not going to memorize periodic table here. We're here to make sure that we can read it. Now, atomic mass is the mass of the protons and the neutrons, okay? Now, given that, the mass, I'm just going to say mass, the atomic mass from here on out. I'm going to save that so that I have it in my stuff saved that way. I just want it that way. It's just the way I want it. Now, what I want to make sure I talk about is let's say I've got the mass. And we know the mass is the number of protons plus the number of neutrons. Now, let's take nitrogen, for example. Now, let's just say we have an atom of nitrogen has a mass of 14. There will be one with that. We're going to make sense of that in a minute. Now, let's also say, guys, that we have the number of protons. Where do we get that? We get it from atomic number. That is 7. The number of neutrons. Now, how do we find the number of neutrons? Well, as it turns out, we know the mass, so all we got to do is the number of neutrons is equal to 14 minus 7. So the number of neutrons would be the atomic mass minus the atomic number, and this will tell me that I also have 7 neutrons. So we can look at this and say that protons equals 7, neutrons equals 7, and electrons equals 7 on an atom of nitrogen that might be here. This does not count any of my isotopes. Now, what is an isotope, you ask me? Well, that's what we're getting ready to talk about, is isotopes. Now, let me kind of explain an isotope by explaining something you probably have already experienced in your life, and that is an exam average. When you take an exam, the average is often told by the professor. The professor might say, or teacher in high school, they might say, I was very disappointed in the exam average. It was a 60. Now, that doesn't mean no one made an A, and that doesn't mean the lowest grade was a 60. That means somebody could have made 20, and somebody could have made a 100. It just says on average, the grade was a 60. Now, you could be above that average, you could be below that average, or you could be exactly average. Now, what we want to help you understand is that some people did better than average, okay? Now, let me kind of use our good friend carbon to explain this phenomenon. And what we're going to do, we're going to talk about normal atom of carbon. And then we're going to talk about some isotopes of carbon. Okay. Now, the mass, let's say I've got a mass. Let's say I've got the number of protons and the number of neutrons, and let's look at number of electrons. Now, we have what is called carbon 12, carbon 13, and carbon 14. These are the isotopes. Now, the mass is the number we see here, okay? Now, we all know carbon should always have 6 as its number of neutrons in a normal element. 6 is the number of protons based on what we saw here. So we would say 6 because 6 minus 12, but 6 minus 13, we got a different number, but also it's again 6. Now, we will also see charge is the same. They all have a charge of 0. Where do they differ is their number of neutrons, which affects their mass. Okay? It is like if I had a balance here and I was weighing out a bunch of things here, okay? And that I had all these protons and neutrons that I was weighing out, okay? And I have the protons and I have the neutrons, and this will create a mass because these two are different. When you add more to it, you're just going to make the mass go up, okay? That's what we're doing here, okay? Hope that makes sense. Now, what I want to help you guys understand is extra neutrons. They have the same chemical properties. They'll behave the same in the body, but they will have extra mass, and they are called isotopes. Isotopes are elements. They have the same number of protons, but they have different numbers of neutrons. And what they will do, guys, they will behave the same. Some of them are radioactive isotopes. They decay. They can last for a short, brief amount of time. For example, francium has a very small half-life, but 50% of it is gone. Decay 50%. It's called a half-life, and we talk about that. These are for unstable radioactive isotopes. Now, they can be used to treat cancerous tissues, things like that. Like in thyroid cancer, you might use radioactive iodine to treat thyroid cancer. All right. Now, what I want to do is help you guys understand something very complicated. And before I do, we have to understand that our electrons are living in shells. They're housed in shells. Now, let's say I've got a nucleus. Now, I want you to think of the nucleus. Think of this as the mall. Okay, think this is the mall. Okay, and you want to go shopping at the mall, and you're hoping to park really close to the mall. And they have a parking lot right here. And this parking lot number 1, there is only 2 spots there. That's it. You got 2 parking spaces. Okay. You could see that number 1 can only hold 2 cars in it. Now, let's say I go in, guys, and I have lot number 2. Now, lucky for us, lot number 2 can hold a lot more. It can hold 2, 4, 6, 8 cars in it. And then if it's full, we have to go all the way out to parking lot number 3, so far away from the mall. And it can hold up to 3 until you get to argon. Once you go past argon on the periodic table, it starts to hold 18. Rules of quantum mechanics say it can. Now, so the third one can hold up to 8. Now think of this as a parking lot where these parking spaces are all that's there. You cannot park anywhere else. The laws are very strict. You can park nowhere else. Okay. Now, what we want to help you guys understand is first we have to know that these are the rules for parking. These are the number of lots that you have. Now, how do you park? You wanted to park as close as you could to the first lot first. So you went and you would fill up lot number 1. When it's full of 2 electrons, shell number 1, it can hold no more. You have to then go out to shell number 2. and it holds 8. Once it gets to 8, it's full. You must then go out to lot number 3, shell 3, and you fill it from the inside out. Okay. Now, let's say I have here, let's take one of our classic examples here. I think that's right, 12.01. I am guessing sometimes on these. Without looking it up, I don't like to just fly by the seat of my pants. I'm not that kind of person. But 12.011. Okay. Now, let's say I have a nucleus of carbon right here. Now, let's take shell number 1. Now, first things first. We know that it has 6 protons, but we also know it has 6 electrons. Now, let's take 6 electrons. Let's put 2 of them in the first shell. We have taken away 2. We now have 4 electrons left. So where are those going to go? Well, we then move to the second shell. The second shell can hold up to 8. So we're going to go 1, 2, 3, 4. And what we're going to do is we've filled this guy up as much as we can to its outermost shell. Okay, let's write this another one. Let's do nitrogen. We've done nitrogen before. Let's talk about nitrogen. Okay, nitrogen, 14.007. Okay, so we know that it has a certain number of, it has 7 protons and 7 electrons. Okay. Now, let's take this guy and let's try to park these around the nucleus of this nitrogen atom. Shell number 1 will be holding 2. Okay, we know we have more than 2. So we have 7 electrons. We took away 2 electrons. Now we know we have okay, so we know we have 5 left. Okay, we know we have 5 left. Okay, so what I want to do is, it's about to draw out the wrong thing. I was having to calculate in my head here, and I don't always feel comfortable. Okay, 2, 3, 4, 5. Okay, in the second shell. All right, so what we're going to do, guys, is to help you understand that, is we start on the inside and work our way out. Let's do one in a little bit with a third shell. We'll do this in a little bit when I talk about some reactivities and things like that, okay? So we will do some more of these in a moment. Now, what I want to do is kind of turn our attention back to my notes. Now, all right. Now, so we have a shell, an orbit that each electrons can fit in. The electrons of the outermost shell, called the valence shell, determines all the chemical reactivity. Now, the valence shell, what I want to help you guys understand, is the outermost shell. It doesn't matter if it's only got 1 shell, 2 shells, 3 shells. If it's only got 1 shell, the first shell is the outermost shell, valence shell. If it's got 2 shells, the second shell is the outermost shell, valence shell. If it's got 3 shells, the third shell is the outermost shell, valence shell. If it's got 7 shells, the 7th shell is the valence shell. You catch my drift? The outermost shell is always called the valence shell. Now, there is a maximum number you can hold, and this maximum number I can hold is determined by the rules of physics. Now, the maximum, 2, 8, 8. Now, the maximum for third shell is actually 18. 18 is the maximum, but you're only responsible for those who hold up to 8 in the third shell. Now, we always start 2 goes in the first, remaining goes in the second shell. If there's any more, they go to the third shell. Okay, you start from the inside, you go to the higher shells until the low. You always fill the lower shells first, and then go to the outer shells, the higher shells. And you can see this here. You can see that hydrogen, we filled, go to helium, we filled the first shell. Then the first shell's full, we go to the second shell. We start putting electrons in the second shell, da 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 da, until we get to neon. And then after neon, we start to fill these up again. We got sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Then we're full again. And then we'd have to have a 4 shell. Now, we are not responsible for anyone after argon in this course, just for ease of understanding, okay, because things do get different when we get to like a lot of the transitional elements. Now, what I want to help you guys understand as well is the energy these electrons have. Now, these electrons contain energy. Electrons are energy. They have energy, the capacity to change things. Now, electrons being energy, because they are negatively charged, they're being pulled in to the positive nucleus, being held inward. Now, that hold inward, the further you get away from the nucleus, the more energy you have, because the more you get away from this. So the outermost electrons, the outermost shells are the highest energy levels. So sometimes we can actually refer to the shells as an energy level, because those electrons in the first shell have the lowest energy level, second's kind of middle. The outermost shell is always the highest energy electrons you can get. So the further from the shell, the further from the positive nucleus who is pulling electrons inward, the more energy those electrons have. Okay? Now, we'll talk about valence shell and filling and things like that in a minute. Now, an orbital is just a three-dimensional space where an electron is about 90% of the time. About 90% of the time, it is in a space like these orbitals. Like the first shell has the 1s, second shell has a 2s, and 3 2p's. So if you were to superimpose it, we would say it has 1s, 2s, 2p. You're like, what? That is something in chemistry you will learn, and it never makes any sense to students, so I hope I can help you make a little sense of it here. They always have 2 electrons. There's an electron pair, no more than 2 anyway. They can't hold more than 2 electrons in one orbital. So each of these orbitals here contain electron pairs, okay? And we don't know where an electron is at any given moment necessarily. This is the Heisenberg uncertainty principle. Good old Heisenberg. I saw where a school actually, they meant to put different famous scientists up, and somebody was going to put a picture of Werner Heisenberg, so they searched for Heisenberg, and they ended up putting a picture of Walter White from Breaking Bad up instead, which cracks me up. Now, no more than two can fit in there, okay? Now, let's talk about shells and filling. And to explain this at first, let's imagine that we all went to eat at a pizza buffet. I always use the one nearby campus. Nearby campus, we had this pizza buffet, so you can imagine that'd be popular with some college students to go by, get all the pizza you could want to eat. All you care to eat, really, instead of all you can eat, all you care to eat, sometimes it is. But no, I do enjoy the pizza there. I'll eat it all. I mean, heck, it's not bad pizza, and there's a lot of it. So, man, I like chowing down on pizza. I used to out-eat the football players in high school when it came to pizza. I was the skinny kid that ate like a crazy person. Now, what I want to help you guys understand is that outermost shell is always called the valence shell, and those electrons are called valence electrons, and they determine the reactivity. Now, what does pizza buffets have to do with electrons? Outermost shells are going to be like you guys at a pizza buffet. Now, if we got one student who goes in there and eats all the pizza, and we never seen a man eat so many pizza slices, okay? He ate so much pizza, hardly anyone got to eat. And that person is so full and so stuffed with pizza, they can't eat anymore, but you didn't get. You're unfulfilled. And since you're unfulfilled, you're going to be reactive. You're going to want to try to bond to other atoms to try to get electrons into your valence shell. But if the owner of the pizza buffet comes by and says, hey, I would like to give you free pizza because I've never seen anyone eat so much pizza. They would go, no, I couldn't possibly eat any more pizza. I'm so full. And they would turn it down. But you who are hungry are going to say, give me that pizza. I'm going to eat it. Okay. Now, let me help you guys kind of understand this. Okay. What's going down. Now, I'm going to click on that. Okay. So let's pick a couple elements here. Okay. Now, what I want to do, let's pick one. Let's pick oxygen, number 8. Oxygen, number 8. Okay. Oxygen. Okay. Now, what I want to do, guys, is to help us understand this. Oxygen, number 8. Now, we're going to start with 8 electrons, okay? Now, here we are, the nucleus of oxygen, the first shell. Shell number 1, we're going to put the 2 electrons in it. So we got 8 electrons. We took away 2. And we are left with 6 electrons left to play with. Now, these 6 electrons we have left to play with, they are going to now be able to go into the second shell. Now, we know the second shell here can hold up to 8. So we've only got 6. 2, 4, 6. Okay? Now, what if I did another element here? Let's pick another one. Let's pick neon. Let's pick neon, number 10. Neon 10. Oop. Now, a nucleus of neon. Let's take it without writing it down first. We have 2 electrons here. See, we have 5. Let's see, we have 8, 9, 10. Ah, there we go. A filled outer shell. Now, what does this mean? Valence shell. Valence shell. This one is not full, so it is reactive. This one here is full, so we say it's inert, non-reactive, okay? So we get to kind of play around with those. Let's try another one here. Let's do sodium. Sodium, number 11. Should I make a sodium joke? Nah. Okay, now, 2, 4, 6, 8, 2, 4, 6, 8, 10. One more, third shell goes out. So first, second, and third shell. And then 1 right here by itself, okay? So we can determine reactivity because if you are reactive, your outermost shell is not full. It will not hold the maximum number, 288. So if you have the rules, then you'll know how to do this and understand it instead of memorizing your way through things, okay? So reactive, if you have an unfulfilled valence shell, if the valence shell is full, you're inert or not reactive. And these guys here, all of these guys are non-reactive. These are all inert. Everything else is reactive. These guys tend to react very aggressively, and so do a lot of some of these guys like to react aggressively too. The alkalines love to react. The fluorine is pretty greedy for electrons, so that these guys do not react. They're the noble gases, and what we're going to do is stop here because this is a great stopping point for this lecture. And while I do, I've got a couple questions before I get started. Here, a couple questions I might want to ask you guys, and here's one that I always like to ask students and get them to think. First off, ah, 26. Okay, how many protons? How many protons? Pause, see if you can figure the answer. All right, guys, welcome back. If you said 26, you're right. Why? Always lowest number. Okay. You see what I did there to you. All right, here's another hard question. What element on the periodic table has the greatest charge? All right, give that a second. All right, did you pause and come back? Good. If you did, let's see what you got. None. Why is it none? They all had the same charge. All atoms are fundamentally have the charge of 0. All are neutral, okay, because they all have the same number of protons and electrons. All right, guys, that's some good tricky questions there to end off this lecture. Thank you guys so much. I hope you learned something today. If you haven't, go learn something. And but as always, thank you so much. I look forward to seeing you guys again on Fridays and Honors Bunch. So thank you. Have a great day, and we'll see you in the next one.